land submerged by these floodwaters could be European or Asian or American, because severe destructive flooding like this can happen almost anywhere in the world. Among the most flood-prone areas are the coastal lands bordering continents and islands. For beachfront residents of Southern California, when the high winds of a Pacific squall come ashore during the year's highest tides, it is the worst possible combination. The resulting high waves break on the coastal cliffs and beaches, where the water tears away the sand and rock. Homes built at the edge of the sea become unwilling victims of the battering surf. Their wooden supports are no match for the millions of tons of water that hammer the shore. The waves quickly transform homes into rubble. Along the coastal strip, heavy rains overcome the soil's ability to absorb moisture. And on the hillsides, the saturated soil is heavy and unstable. Water has completely filled the available pore space and has even percolated down to the dense lower layer of clay. Here, the water acts as a lubricant between the clay and the overlying earth. Eventually, the soggy soil breaks free and starts to move. Pulled downhill by gravity, more and more soil oozes and flows, and finally the entire hillside collapses in an avalanche of mud. The residents now find themselves trapped between the relentless pounding of the ocean on one side and the liquefied hills sliding toward the sea on the other. Homes built on the cliffs were safe from the waves and mudslides of this storm. But even here, the protection is temporary. In time, these residents will find themselves at the cliff's crumbling edge, waiting for the inevitable storm that will topple their homes to the beach. Although little can be done to protect coastal residents from floods and mudslides, there is a network of tools that can give early warning of severe weather, and thus a chance to save property and lives. This is the National Weather Service field station near San Francisco. 850 kilometers overhead is the station's eye in the sky, the NOAA 9 satellite. Every 12 hours, as NOAA 9 passes in range, the station's dish antenna is directed toward the signal the satellite transmits. The signal sent by NOAA 9 is a record of the Earth's surface temperature scanned by an infrared sensor on board the satellite. The satellite-generated image of the Earth received by the weather station shows the distribution of radiant heat. The warm west coast of the North American continent is the dark blue mass to the right. The cooler Pacific Ocean is the lighter colored area to the left. The surface maps generated by the satellite give meteorologists an important perspective on the dynamics of weather, a global view. They can track a storm's development from its birthplace, far out at sea, to its potentially destructive approach to the coast. 24 hours a day, 7 days a week, changes in the atmosphere over the Pacific are monitored. Advanced knowledge of the severity of a developing storm provides an important basis for forecasting coastal flooding. The most dangerous weather systems are large, intense, and slow-moving, since they can linger at one location and batter it for days. The same weather system that brings rain to the coastal strip may drop snow in the mountains inland. There, a heavy snowpack sits like a loaded gun, and a few days of unseasonably hot spring weather pulls the trigger, causing intense snowmelt to pour out of the mountains. Downstream, residents can find themselves flooded by snow waters dropped months before in mountains tens of kilometers away. Block by block, Salt Lake City has been built in the path of snowmelt runoff from the surrounding mountains. Although culverts and other provisions were made to carry the flow, the meltwater of a snowy winter followed by an extra warm spring has overwhelmed the city. Following its downhill course, the water reclaims its natural paths and flows over old creek beds that are now asphalt-covered streets. The annual snowmelt and rain from nearly 800,000 square kilometers of the Rocky Mountains flows to the Colorado River through a huge network of creeks and streams called the Colorado Basin Drainage System. To gauge the extent of the western snowpack, each month surveyors from the U.S. Soil Conservation Service fly to 1,500 backcountry sites during the winter to spring. Samples are taken with a long aluminum tube which is driven into the snow. The length and weight of the plug of snow in the tube is an indication of how much water will be released during the spring melt. For the 4-centimeter diameter tube, every 30 grams of snow is equivalent to 2.5 centimeters of water. The monthly snowpack data is sent on to the Colorado River Basin Forecast Center in Salt Lake City, where, along with other lines of environmental information, it becomes part of a computer model designed for flood prediction. Dr. Gerald Williams is the hydrologist in charge of the Colorado Basin Center.
To generate flood forecasts, we need hydrologic information under the current conditions, that is now conditions. This would include snowpack information, the expected temperature information, precipitation or rainfall information, and all of this is entered into the conceptual hydrologic models to generate the expected river flow for the next few days.
Twice daily, instrument-carrying balloons are released. The atmospheric data they gather is used to predict weather conditions. The resulting temperature and precipitation forecasts, in turn, become critical factors in the calculations of expected snowmelt. The balloon's flight path is tracked from the ground. Meanwhile, the balloon's instruments signal back the humidity, temperature, and barometric pressure as it rises to the upper atmosphere. Simultaneously, all across the country, dozens of other weather balloons are released. Together with balloons released worldwide, meteorologists are able to construct an up-to-date composite picture of the global atmosphere. In addition to satellite and balloon-gathered information, river flow and precipitation readings are collected automatically at more than 2,000 recording stations around the country. Several times a day, many stations in the Southwest beam their readings to a satellite to be later transmitted to the computer at the Colorado Basin Forecast Center. The center issues flood warnings to all downstream locations in the drainage basin. And this year, the residents south of Salt Lake City will be among the first to get the bad news. This season's snowmelt is a deluge. The water spreads in a fan 2 kilometers wide and 25 kilometers long, covering the flat rural countryside. Sandbagging here does little to protect homes and businesses from the shallow sheets of water that come from all directions. After decades without a serious flood danger, a rare combination of snow and heat finds farmers unprepared and helpless to respond. Further downstream, 75 kilometers south of Salt Lake City, day after day of rain and snowmelt saturate the mountains. Heavy with water, the liquefied soil flows, and blocks of boggy earth slide over the slick underlying bedrock. Finally, a landslide more than 2 kilometers long breaks free and rolls into the river valley, creating a natural earthen dam. With its course through the valley cut off, the river begins to fill the valley behind the landslide. Quickly, heavy equipment converges on the slide. They work to reinforce and stabilize the new dam. If the dam fails, the water trapped behind it will be released, and everything downstream could be washed away, including the city of Spanish Fork. With millions of tons of water pressing against the slide, it could collapse at any time. The gamble pays off. The new dam holds, and a new lake is formed. But a heavy price is paid for the success. Trapped on the wrong side of the landslide, the small town of Thistle is drowned in the rising water. Homes torn from their foundations are floated to the surface. Slowly, they drift with the sluggish currents like a fleet of ghostly derelicts. Located near the headwaters of a rocky mountain stream, Thistle was thought relatively safe from flood danger. But in an instant, nature altered an ancient watercourse, and Thistle was gone. A rare desert thunderstorm. The rain rolls off the rocky terrain and into the gorges. More and more water collects, and a flash flood sweeps down the canyons toward the desert floor. The foamy wave engulfs everything in its path and scours the sandy soil into a thick slurry. In the uninhabited desert wilderness, the drama goes unnoticed. Just another episode in the always changing landscape. But in other areas, washes and floodplains may be the site of housing developments or freeways. Still, with planning, we can provide for the flow of the water. Dams built along the Colorado River, for example, have reduced the number and severity of downstream floods, and even conserved water, precious in the arid region. This is Davis Dam in the western Arizona desert. It's ironic that one of the driest regions in the United States needs a dam to protect it from flood danger. The flood danger here is not from a local threat. It starts as the snowpack of the Rockies, 500 kilometers away. And sometimes, even the dam is not enough to stop the water. A late-season snow, followed by fast-rising temperatures and heavy rain, has produced a quick thaw. The torrent that is on its way is 1.5 times the capacity of all the dams along the Colorado. The residents are warned. The floodgates must be opened, or the dam will be overwhelmed. The water released by the dam washes over the low-lying riverbanks and spreads across the floodplain. Seeping into the ground, the floodwater lifts waste from cesspools to the surface, and dangerously contaminated areas must be cordoned off. The only chance to save property from the rising water is sandbagging. Before the construction of the dam system, snowmelt flooding like this was an annual occurrence. Most of the building in the floodplain took place after the dams were installed, after the dams took away the yearly reminder that this land is a watercourse. Now, a few weeks of hot weather in the mountains 500 kilometers north, and the river has reclaimed its route. Even with the floodgates wide open, 3 times more water pours into the reservoir than can be released. Now there is a danger that the reservoir capacity will be exceeded. If it is, water will pour over the dam's spillway, and the flooding will be double or triple. Further downstream, the floodwaters have now reached farmlands in southern Arizona. After dropping 4,000 meters from its origin in the mountains 1,000 kilometers north, the flood finally reaches sea level. As the water crosses the border into Mexico, the International Boundary Commission monitors the river flood conditions. Local volunteers work to stabilize dikes, protecting farmland and homes. The floodwaters have now lost most of their destructive force and have become a slow-moving pool spreading over the broad Mexican marshlands. For nearly 50 years after the construction of Lake Mead, this area was spared from the once common floodwaters. But as river sediment has reduced the storage capacity of Lake Mead, the snowmelt water again returned to this floodplain. The route of the Western Rockies snowmelt includes only a few of the flood sites in the United States. Almost every region suffers occasional or frequent flooding. Probably the most regularly flooded spot in the U.S. is the lower Mississippi River Valley, and in particular, the Louisiana Bayou country. In the bayous, flooding is part of the rhythm of life. The swamps and marshes are here because this place has been the floodplain of the Mississippi for thousands of years. Each spring, much of the snowmelt and rain that has fallen on the central third of the country, from the eastern Rocky Mountains to the Appalachians, drains into the Mississippi. Eventually, this enormous quantity of water flows through the bayou country on its way to the Gulf of Mexico. Everyone knows it's coming, and everyone prepares as well as possible. But because the route of the floodwaters is so flat and wide, controlling the water with dams is impossible. Instead, a network of levees was designed to channel the flow safely around the towns, and usually they do. But this year, the levees are no match for the quick thaw in the Rockies. The river continues to rise. The Flood Forecasting Center issues another warning. The expected crestwater will be higher than the riverbanks and primary levees. Now, even the dike-protected lowlands are threatened. Delta farmers have been through it many times before and respond almost automatically. All equipment that can be driven or trailered is moved to high ground. Now the vigil begins. Will their homes and crops rooted in the lowlands survive the flood? Will the high ground they have chosen be high enough? The water tops the river channel, marked by the dense tree line, and pours onto the floodplain. And once more, the low-lying bayou homes and farms are covered by the murky flow. For hundreds of centuries, floods have plagued civilization, and it is likely that we will never completely control their destructive flow. But thanks to dedicated scientists using satellites and computers, we can at least provide flood warnings. Today, we can predict a coming flood. Now we are given time to prepare for the irresistible torrent to reclaim its natural role in the Earth's cycle of water.